So let us get started with the approximation of functions. A multilayer perceptron that is trained through the backpropagation algorithm can be an engine for learning the input-output mappings. And I would like to emphasize nonlinear input-output mappings. Linear maps are anyway affine maps, and you can learn that using the perceptron, but this is a nonlinear input-output mapping. So what it means is, if I have inputs in R m naught, then I can think of a mapping from R m naught to R m suffix L. This is the space of output neurons. And this relationship is basically a mapping from two different Euclidean spaces. Now the question that we will have to look into algorithmically is, what is the minimum number of hidden layers needed for a multilayer perceptron to learn the input-output relationship. Right? This is what we are given in a machine learning problem or supervised learning problem. I give you some inputs, I give you the desired response, I need to learn the mappings. Right. So a natural question is, we have learned the multilayer perceptron, there are neurons in each hidden layer, how many layers do we need? Right. Fortunately, there is an answer to this question, and the answer to this is in the universal approximation theorem. So let me state the universal approximation theorem, and I will cite the references for this, that you can delve into the details of the proof, and time permitting we will cover this proof in a later module. So let me state this result. Let phi be a non-constant bounded and monotone non-decreasing continuous function let I m naught denote a m naught dimensional unit hypercube the space of continuous functions on this space I m naught is denoted by C of Im naught, indicating they are all continuous functions. Then given any function f that belongs to this space, that is the space of all continuous functions on this unit hypercube, and for some epsilon which is positive, small positive epsilon, there exists an integer m1 and sets of constants alpha I, bi, wij for I equals 1 dot 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 till m1 and j equals 1 dot 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 till m naught, such that this function over these variables 1 to m naught can be described in this form. So, this is an approximation of the true function over these m naught variables, such that the absolute value of this function, which is approximating function, minus the true function, is within epsilon. Okay. So, this deviation is within epsilon. Now, what this means is, if you can see the connections of the form of the approximating function that I have written down here, right, maybe I will erase this, right, you just focus on this approximation function. This has some scalars alpha I, and then you have a nonlinear function phi here, right, and you know you have a local, this is like a local receptor field that you have, because you have some weights that scale the inputs, and then you have a bias term that is adding, and then a nonlinear function acting on it, and there are m1 such nonlinear functions, and you scale them by this parameter alpha I, and maybe you can make a decision on top of it. So, let us forget the decision step at this moment, right, that is what you have it as desired, but you can, using this form, you can approximate the function, right, the true function. And the hint is that you can use these hidden neurons, and a single layer of hidden neurons will suffice for approximating this continuous function, and that is the key. So the key is one single layer of hidden neurons will suffice. So we don't have to have multiple layers, but we can have one single layer of neurons, and this will suffice to learn this IO mapping, and that is the key idea behind the universal approximation theorem. But nothing is told in this theorem regarding the optimality of a single layer with respect to the learning time, the ease of implementation, the generalization of the order in an input process, that is, if the input process has memory, what is the order required, etc. Nothing is told about this. And how many neurons we require, we just mentioned that if we have M1 neurons it suffices. It does not tell how this is dependent on the data point density, right. And these are all the suppositions, these are the details, but the gist of the theorem is that we can approximate any continuous function in an M0 space using a single layer of hidden neurons. Okay, the details of the proof of this theorem are in two special papers which will be provided, and time permitting I will cover the proof of this theorem towards the later part of the course. Now with this approximation that we have using a multi-layer perceptron, and we see how using the MLP we can approximate the function, let us delve slightly into the bounds on approximation errors. Barron in 1993 established the approximation properties of a multi-layer perceptron assuming sigmoid functions and a single layer of hidden neurons, right. He established the approximation properties of a multi-layer perceptron using sigmoidal functions and a single layer of hidden neurons. When given a set of data points sampled from a function, the network gives an approximating function, right. Suppose f is the function representing the data points, right. This is basically the true function. The network gives us the approximating function, call it f. I call it f. Now when the network is exposed to test the data, the network function, which is this function, the approximating function capital F, acts as an estimator of the new points of the target function, right. We can say that f, I will put the approximation sign here, is approximation of the estimate of the true function. So let us set the context here. Let f tilde of w, w is a vector, denote the multidimensional Fourier transform of f of x. X is a data vector and f tilde of w or omega, whatever you might want to call it, let it denote the multidimensional Fourier transform, and this data point belongs to this space Rm0, right, and w is the frequency vector, right. You have, if it is a 2D plane, you have omega 1 and omega 2 or w1 w2 as the frequency coordinates. Now f of x can be obtained using the inverse Fourier transform for a complex valued function. F tilde of w, for which w times f tilde of w is integrable, let us define a parameter Cf, which is the first absolute moment of the Fourier magnitude distribution of f given by this equation. This is the first absolute moment of the Fourier magnitude distribution of f, and in a way this quantity Cf qualifies the smoothness of this function f. I would say that Cf in a way measures smoothness of f. Now we have the following theorem from Baron, which basically provides a bound on the empirical risk based upon this parameter Cf. So let me get into the details of this discussion. Consider a ball which is b suffix r, which is a set of all points x such that the norm of x lies within a radius capital R, small r. The norm of x lies within a radius small r, and we assume r is greater than 0. So the theorem due to Baron is stated as follows. For every continuous function f of x, that is function acting on the data vector with finite first moment c suffix f, and every m1 which is greater than or equal to 1, that means I should have at least one such unit here. There exists a linear combination of sigmoid based functions. These are our approximating functions capital F of x, such that when f of x, which is the true function, when f of x is observed over these inputs x, right, you will have these exemplars xi I equals 1 to n restricted to this ball b suffix r. The empirical risk is given by this equation. This is a squared error between the function evaluating on the data point and then the approximating function acting on this point. This squared error is less than or equal to this quantity 2r c suffix f square 2rcf the whole squared upon m1. Okay, and this is a very important result, that this empirical risk is bounded by this quantity. So, I give you a bunch of data points. If I know m1 and if I know cf, that I can compute based upon the Fourier transform of the true function, and computing that itself would require some sort of estimate, and if we have that estimate and we can compute cf, then the empirical risk is bounded by this quantity. This is a very important result. This sets a bound on the number of hidden neurons that we may require, and that is the reason why this theorem is useful. So, if we further simplify, which is what Baron did in his paper, this quantity is of the order Cf square upon m1 plus order of m0 m1 upon capital N log n. So, this is the number of examples or data points. M1 is size of hidden neurons, and M0 is our input space, which is where the data points reside. Right? This is a sort of a bound, and what stems from this bound is this quantity m1, which is sort of approximately Cf times n upon m0 log n, the square root of this quantity. So what does this mean? That there is a dependence on the rate and the input dimension, rate of this error and the input dimension, right. So if I simplify the average error, this is further simplified as where S is a measure of smoothness and m naught is this quantity which depends upon the input dimension. So what really it means is the following: that the sampling density is proportional to the m naught root of the number of data samples. That is, the sampling density is proportional the sampling density is proportional to the m naught square root of the number of data points. What we mean here is we need to densely sample the data points to learn the function well, right. I give you a higher dimensional space, I need to sample these points densely in a higher dimensional space to learn this function pretty well, right. But there is an exponential growth in complexity due to higher dimensions. So there are trade offs here, right. So to learn the function well, I need to sample the data points from higher dimensions, and at the same time higher dimensions implies exponential growth in the complexity of the network or algorithm or whatever we want to call this here. So we are faced with this problem, and this is basically called the cursive dimensionality. But at the outset, going to higher dimensions can help us because we have more generalization ability and we can kind of separate these patterns pretty well. So going to higher dimensions is useful for us, but if we go to higher dimensions, we have to densely sample the data to learn the function well, and this also leads to increased complexity, right, and this can be exponential, the increase is exponential. So therefore we have this trade off. So this point on cursive dimensionality will be again addressed when we discuss Cover's theorem, and again we will see there what is this trade off in going to higher dimensions, and how is the behavior in terms of learning the function, learning the input output mapping in terms of the approximating function, and the generalization abilities that we can get for pattern separation and pattern classification problems. Okay. So this sort of covers some of the basic ideas related to the backpropagation algorithm, right. I think what is important is we can have a single layer of hidden neurons that can give us a pretty good generalization in terms of the input output mapping, and that is the key idea. but in practice we may go with multiple layers because we do not know how many number of nodes to choose in our hidden layer to get a very good approximation. So, since we do not get a direct handle, we kind of use a cascade of these hidden layers and then we try to approximate this function. Okay. So, let us stop here. We will continue on with a few other technicalities related to this algorithm in terms of Jacobian and Hessians, and we will talk about this in a short while.